This is the same talk that I gave a few days ago at the big National Computer Security Conference in Philadelphia. This is peer-reviewed and published research. Okay, this is collaborative research done with Casper Rasmussen at the University of Oxford. So the context here is status indicator lamps. We want to figure out a way to hack into a completely isolated computer just through an LED indicator. So if you shine a really bright light on one of these status indicators, that energy has to go somewhere. Would you believe it flows backwards into the electronics? Effects range from nothing at all to remote code execution. It takes a fairly powerful laser to do it because in addition to information, you are also supplying all the energy needed to run the electronics in reverse. There are at least two different physical effects at work, a photoelectric effect and a photoconductive effect. The photoelectric effect lets us change a binary 0 to 1, but not the other way around. The photoconductive effect lets us change a binary 1 to 0, but not the other way around. This immediately suggests that the two effects might be used in concert, but there's a problem. Some electronic components respond to only one effect or the other, but not both. So this places some fascinating constraints on the attacker. Those bit patterns over on the left-hand side are all the possible assembly language instructions for an imaginary computer. If we assume you can only change a binary 0 to 1, but you can never go the other way around, then some of those instructions are reachable from other instructions. As you can tell from the graph on the right, the attacker might be able to change a load instruction into a branch or an add into a subtract, but we can't change a branch into a store or a divide into a compare. So we say the attacker can only execute arbitrary-ish code. So our attacker patiently watches the instruction stream go by on the bus, picking and choosing opcodes that he can alter into the instructions that he wants, slowly building up the desired program in high memory. Maybe it's not quite the program that he wanted because some of the bit patterns were unreachable. So the first thing the arbitrary-ish code does up in high memory is run fix-ups on itself. Finally, we redirect a branch and it's game over. The attacker must be very careful never to crash the running program because its memory accesses are needed to subvert. If the target computer ever crashes, access is immediately lost. So maybe I should demonstrate. This is a fairly simple computer, but it's complex enough to illustrate the difficulties. It's 4-bit CPU, load-store architecture, running the instruction set of the previous slide. It has one register called the accumulator, which is visible on the front panel, and that's important. Think of this as a factory automation controller, reading temperatures and pressures, sending commands to motors to do open and close valves in a chemical process plant, say. Normal operation of this computer is shown by a regular scanning pattern on the red LEDs on the right, just 1, 2, 3, 4, 1, 2, 3, 4. The attacker needs to watch the target system for a while, learn the timing, and establish a phase lock on the internal state of the CPU. This is possible because the accumulator display always changes at a known offset in the microcode cycle, which might be different for different instructions, but the attacker can tell the difference by observing the direction and magnitude of the change. So the attacker just watches, measuring the cycle time and getting a phase lock on the microcode cycle. It takes about 10 iterations of the program through the program to get a phase lock. Timing is absolutely critical. Once the attacker has got a phase lock, the lasers begin firing. The beam is invisible because these are ultraviolet lasers, but you might be able to see a little bit of fluorescence in the clear epoxy over the LEDs in the middle, the green LEDs. This also serves to illustrate the general principle that you're not always shooting at the same LEDs you're watching. It only takes a couple of seconds, but note that the pattern on the accumulator LEDs over on the right-hand side has changed. It is no longer doing the regular 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4 pattern. And that's because this computer is now running a completely different program that we inserted through the status LEDs. Analysis begins with the electrical schematic, looking for potentially susceptible components in electrically interesting places. This is another of the constraints on the attacker because we can't choose where the hardware designer may have decided to put LEDs or how they're connected. And that determines what we can do. Not every indicator will do something interesting if reversed. So here's a typical electronic component. Light emitting diodes are interesting because they are a naked PN junction, the basic building block of all solid state electronics. You put electricity in, light comes out, in this case, pink light. But there's a general principle in physics that any process that runs in one direction can often be made to run in the other direction if you supply enough energy to make up for the difference in entropy. When you put light into an LED, it comes out as electricity, but in the opposite direction from the usual current that makes it light up. This violates some important assumptions made by the hardware designer. We can force the voltage on a communication bus low or high, depending on how the LED is connected. So if the eyes are the windows to the soul, LEDs are a window into the electronics. Now, the first question everybody always asks is, how far away can you do this? And the answer is, we don't know. I didn't put this in the paper, but the reason we don't know is because I'm blind and I suck at aiming. It is not my problem to figure out how to aim this thing. It's my problem to measure it. So we built this infernal machine. It consists of a pair of linear actuators with the x-axis bolted crosswise onto the y-axis. We basically built a little 3D printer. Allows us to raster scan a focused laser beam over any circuit component, over any desired component on the circuit board. The scans that we do are very, very tiny, typically 1 square millimeter, but we stop every 50th of a millimeter along the raster scan and measure the voltage on the bus. There's a live I²C bus running underneath all of that, and it's just communicating all the time. So we make these scans, the data collection is automatic, goes out through a serial port, and then we analyze it. Here's what the raw data looks like from one of those scans. The big blue square is 5 millimeters across. So this is a tiny little scan, it's this big. You're looking straight on into the LED, and that funny looking curvy arc over to the right-hand side is an artifact of the dome lens on the LED, we think. We can draw isovoltage contours to help try to visualize what's going on. We're measuring the voltage as the laser scans across the LED, and we're looking for the place where we can force the voltage on the bus by that rainbow scale on the right-hand side. We want to force that voltage down below some critical value. And the only contour that we're really interested in is the one at 2.0 volts, because that was the critical value that we found by experimentation. This is the picture where Professor Rasmussen got really excited. He calls this the active area. Any hit by a laser inside that contour changes the value of a bit. He wanted to know the area inside that curve so that we could do statistics on it. Oh, finding the area of that curve is one of those problems in computer science that looks hard but isn't. You look at that and you think, oh, we're going to have to, it's a double integral. And no. It's really easy to find the area inside that curve. You just sum over all of the pixels in the image and count the number of pixels whose value is less than 2. I felt like Alan Turing when I came up with that algorithm. Come on, I am a god among programmers. Don't tell anybody because they all think I'm a whiz at physics, a whiz at calculus. There's a problem though. The designer might not have put an LED where we need it. And you can't shoot lasers at an LED that isn't there. But I don't want to give you the impression that this is only about LEDs or only about status indicators, because it's not. The definition of an accessible PN junction is wider than that. This is a microphotograph of the chip inside an electrostatic discharge protection component, ESD. Now, the circuit designer might not have put an LED on the communication bus where we need it, but electrostatic protection devices are there because shared communication buses are susceptible to static electricity. It's a tiny, tiny little target. As you can see from the magnified view, that chip is only 250 micron, or 125 microns across. And it's not even centered in the gap. It's a very challenging target to hit. And yes, you need line of sight access. But here you can see the results of a lot of repeated runs against the same component under different conditions. And I just want you to observe that the red, the size of the red area gets larger as you go downward in the chart, and it gets larger as you go off to the right. We have a model that makes testable predictions. So given any color of LED, laser wavelength, logic family, and value of the pull-up resistor on the bus, we can predict if it's reversible. So here's another demonstration. Again, this is an I2C bus. This is the demonstration I took to Philadelphia, and they liked it. The owner of the I2C bus is trying to write the words normal operation on the display. The laser is trying to write the words proof of concept. They're fighting. They're fighting for control of the bus. And the laser is generally winning. I just love watching this demonstration because you can see that the attack is clearly feasible, but it's probabilistic. And I just love watching them fight. It's not isotropic. This plot shows the effect of elliptical beam axis rotation on the active area. We have not looked into the value into the effect of polarization at all. Finally, I want to thank the anonymous peer reviewers for being so harsh on us. We got rejected a lot of times. There is not one claim left in this paper that we did not measure to 3 decimal places, and it's a better paper because of it. So here's the reference. It was published just a couple of days ago. The only people in the world who know about this are the people, 1,000 people who were at this major computer security conference, and you guys. Any questions?